Hello, all you happy people. This is Kaveh in Honolulu, and I'm continuing my series of Common Lisp lessons/tutorials. This is lesson 6, and in lesson 5, we saw about groups and nesting transformations, and we're going to have some fun with hierarchies today. So, the basic thing we're going to start by doing is creating some instances of objects. So, before we had a function called scatter shapes, which basically made copies of shapes and put them around in different points in space. What we're going to do here is we are going to create groups and scatter those groups around, but they all have the same shape as their child. So let me show you what I mean. So we're going to evaluate this thing that makes a row, and we're going to basically make a row of circles. So what's interesting about this is that basically here we have 3, 4, 5, 6, 7, 8, 9, 10 circles. And what we really have is we have 10 transforms, 10 groups, each one of which has the same circle. In other words, they're all sharing the same circle. So we can see that if we print the hierarchy, there we go. All right, so we have our scene, and then we have one main group, and then that main group has got 10 subgroups, and each of those subgroups has got a shape. And if you look at the addresses of the shapes, you can see it's the same shape in all cases. And so we're basically, if you remember in lesson 5 in the previous lesson, we had that pentagon that we put into the hierarchy, and it appeared in 2 places because it was the child of 2 different groups. Well, we're now using that on a bigger scale and having a circle be in 10 different groups, but it's the same circle, and it only takes up the memory of one circle. And in computer graphics, we call this instancing, where, for example, if you have, I don't know, say you try to make a forest and you make a tree, and then you can copy that tree around and place it around in lots of different places, but it's the same tree, and you can scale it and rotate it and translate it, but it only takes up one tree's worth of memory. So what are we doing here? We are creating a list which is empty. We loop n times. We create a group that contains one child, which is the shape that was passed in here. And then for the transform of that group, we make a transform that's got to translate, which is p times the spacing of p by ii. So what we're doing here is basically just specifying a number of shapes, a spacing between them, and then the shape itself. And in the previous case, it was a shape function that we were using. So each time it executed the function, it actually created a new shape. Here it's the same exact shape as we can see here from these addresses. And then we put that into the row, push that into the row, and then we make one top level group that we return, which basically is just a group that contains those rows as children. And in our particular case here, we define a global variable called row group, which is nil. And what we do is we set that row group to be a make row group, 10 shapes, translated by 0.2 in x, and it's a make circle shape with 16 points. And then we translate that whole thing by minus 0.9 so that it's centered on our screen, and we add that to our scene. And then what we can do is build on top of that. So we have row group, which is a group which contains these 10 subgroups, each of which contains the same shape. Now, if we do the same thing here, and we create a grid group global variable, and we set the grid group to be a make row group in Y of the row group that we already made. So we're going to take this whole thing, and since it is a shape basically, because group inherits from shape, and we're going to make another row out of it, but our row is going to be vertical in Y. And if we evaluate that, we now have basically a vertical row of a horizontal row of spheres. So say that fast 5 times. All right, if I print the hierarchy, it'll be here. So it's obviously, it's got 100 different groups in there, but we have, this is the scene. This is our vertical group, and it contains 10 horizontal groups. It contains a group of 10 horizontal groups that basically contain one sphere. Well, not sphere, sorry, circle. So the interesting thing is that as we look down this thing, all of these addresses are the same. So we're essentially placing this circle of ours in 100 different spots in the hierarchy. And all the groups are different addresses, but all this circle is the same address. So we're essentially drawing that circle 100 times because it's in 100 different spots in our hierarchy. All right. So let's see what else we can do with our hierarchies. So we had scatter shapes, which basically created shapes at different points in space. So we can basically create another thing called scatter groups. And scatter groups takes another shape function and number of points, so it has pretty much the same signature, except that it creates a group containing those shapes. So let's define that. And if we just try it here, we can see that basically we gave it a function to create a hexagon shape, and we give it 3 points, and it places the hexagons at those 3 points. So these 3 hexagons are basically in a group, and they appear here. So then what we can do is get a little bit clever and say, let's make a recursive group. So a recursive group is basically a fractal, or what we call self-similar object. So we'll see what I mean by that in a second. So the base unit is these 3 hexagons in a triangle. And what it does is basically it calls scatter group with a function to create the shape. And that function is a recursive function. If levels is 0 for the terminal case, it just makes 1 hexagon. And then instances that hexagon or creates copies of that hexagon at these 3 different points. And that's what we currently have here, a hexagon at 3 different points. If levels is not 0, it makes a hexagon trigroup recursively. It calls itself with levels -1. And so let's see what that does visually. So if we compile this, so if we make, if we call this with a level 0, it's the same thing, nothing changed. If we call it with level 1, we get this. So wherever we had a hexagon before, we had 3 hexagons, we now have 3 hexagons. So this is what's meant by self-similarity, which is basically each part of the object looks like the entire object. So this is 3 shapes in a triangle made up of 3 shapes in a triangle, if that makes sense. And if we go with 2 levels of recursion, we get this. And if we go with 4 levels of recursion, we get this. So this is basically a fractal shape where this shape is similar to the entire shape, which is similar to this shape, which is similar to this shape. So each part of it resembles the entire thing, and that's kind of the basis behind fractals. It's called self-similarity. So now we can start having some fun with this and just use our imagination. So for example, if we make something called a make square cross group, and this is our make square cross group. And so we've basically literally just taken a square and put in the coordinates to place it in a plus sign. And that's the base case with 0 levels of recursion. If we want 1 level of recursion, we get this. So you can see that basically this is our original shape, and now it's replicated many times. And if you give it 2 levels of recursion, we get this. So continuing with our explorations, we tried different shapes, different configurations. So this one I call the square X group. So we have again a number of points in an X shape, and we take a square. And the base case is this. And then 1 level of recursion gives us this. And 2 levels of recursion gives us this. So it's fun to be able to just apply recursion and get interesting looking shapes. So then, being a good Lisp programmer, whenever you see a pattern, you have to ask yourself, can this pattern be generalized in an interesting way? And all of our functions here, make X scatter group, and make square cross group, and so on, you notice they have the exact same structure. They have different coordinates, and they have different base shapes, and they may have a different scaling factor between the different levels, but they have the same structure. So what if we can generalize and abstract out that structure and do something interesting with that? So we have a generalized recursive group function. So we make a recursive group by giving it the levels, the base shape function, the points, and the scaling. And it's the exact same structure, and we've just basically put in these variables instead of the constants that we had before for our squares and for our points. So let's see what this gives us. If we take the base case and we give it a square shape on the points of a hexagon, that's basically squares on the points of a hexagon. If we recurse once, 1 level of recursion, we have squares on the points of 6 hexagons. So we have squares on the points of a hexagon. 2 levels of recursion, 3 levels of recursion, and so on. Let's try another case, since this is easy to test out. Let's put a spiral on a spiral. So if we have a level 0 case, the base case, we took our spiral function from one of our earlier lessons, and at every point on that spiral, we're putting another spiral. And if we go 1 level deep in a recursion with this function, we get spirals on spirals on spirals. And let's try another case here where we put hexagons on hexagons. Before we put squares on hexagons, now let's put hexagons on hexagons and see what that gives us. So this is hexagons touching each other on the points of a larger hexagon. 1 level of recursion starts looking like a mosaic tile. 2 levels of recursion. 3 levels of recursion. So that's kind of cute. All right, we'll do a couple more cases here since they're easy to do and want to have a generalization written. And looking at this, it's pretty straightforward to maybe even make a macro out of this to generate these functions that do these various shapes for us. But again, I'll leave that as an exercise to the reader. So this is pentagons on a pentagon, base case, one level of recursion, two levels, and three levels of recursion. And we'll do one more, which is circles on circles. So I have a circle. It's a circle of 8 points, so it's an octagon on a circle of 16 points. That's the base case, one level of recursion, two levels of recursion. So it's kind of like interlinked rings. All right. Now, we had this function called doHierarchy before, if you remember. This was a definition of it. And it would take a function and apply it to every node in a hierarchy, every shape in a hierarchy. And we had two cases for it. One was for the shape, which just calls the function on the node. And the other one was the after method that we used for groups, which called the function on all the children of itself. So let's enhance that function a little bit by adding a test for the nodes. So this is the first time I think we've used a keyword argument. So Common Lisp has optional arguments, keyword arguments, and a bunch of other stuff for the defining functions. So keyword argument, you specify the keyword and then the value, and if you don't, then this is the default value. So the way you use it is basically you give it a keyword, and then you give it the value for the keyword. This is kind of what, if you've done Objective-C, you have these colons in your function calls, function signatures. That's sort of keyword arguments, but not really. I mean, those are basically still arguments that are whose use is defined by the position in the argument list. So the regular arguments, they just use the keyword as syntactic sugar to make things more clear to you. Here, if I had 5 keyword arguments, I can put them in any order I want to in the call itself, because it actually tests for the keyword argument. It's not just the fact that this is the nth argument and this is kind of syntactic sugar. So it actually looks up what this keyword is and then decides which argument that is if I have multiple keyword arguments. That was just a little segue. Now, we've seen our ability to define functions as methods and so on, and since we're basically working in a live image in Lisp, it's allowing us to redefine things and warns us when necessary that things are going to change. So before, we had doMethod, which was a generic function with 2 methods, and it took 2 arguments, a shape and a function. Now it's taking 3 arguments, a shape, a function, and a keyword argument. So if I take this and I compile it, it gives me the lambda list of method. This one, shape t, which is the old one, is incompatible with that of the generic function doHierarchy. So what are our options? So basically, this is the method's lambda list, which I tried to define. And this is the generic function that already exists because I defined 2 other methods before that. So it was self and func, but now it's self, func, and key test. So again, we look at our restarts because this is Common Lisp, and we can recover from errors or continue from errors. And so this is the interesting one. It basically says, remove 2 methods from generic function and change its lambda list. So if I select that, it invokes the restart. It removed 2 methods from the generic function. So basically, these 2 methods no longer are bound in our image. And this is the method that we added to our generic function. So what does that generic function do? It does the same thing as the old one did, except before it calls the function on itself, it tests to see whether or not it should be calling the function on itself. And it'll call the function on itself if either the test is null, in other words, test is nil, there is no test, just call the function, or you call a test on itself and it returns a non-null value, i.e., let's say a true value. And then we do the same thing for the groups using an after method, just like we did before with do hierarchy and after methods. And it simply recursively calls the children with that test. So let's compile that as well. So let's try it. Let's add one of our old scenes. Oops, I restarted my image and I didn't evaluate that expression. So let's go back here and this is the stuff we did last time. So we created all these shapes last time. So let me just reevaluate all these things. Into the hierarchy of group 1. We made a group 2. We added group 2 to our scene. And then let's break it up a little bit by executing some of the things that we did before. And now this is interesting because I can still call do hierarchy without a test because the test argument is optional. So this turns on the show access flag, even though these guys are not bound anymore and there is an optional keyword test argument. But if we omit it, the test is nil and has no effect. So let me just quickly reproduce some of the stuff that we did last time. So I just don't want them to be all overlaid on top of each other so we can see what's happening. So we'll move the square. We'll move group 1. And we'll rotate group 1. That should be good. Maybe let's move group, move it a little bit to the center. And move this a little bit apart. All right. So we have our scene. And the root node is group 2. So it's not been added to the scene because I did it already. Now, if we loop through the hierarchy of group 2 and say scale each node by 1.2, but give it a test. And the test is the node must be of type polygon shape and it must have 3 points. So if we try that, let's see what happens. The triangle gets bigger and nothing else changes because the triangle is the only thing that satisfies those conditions of being a polygon shape and having 3 points. So if I change this to 4, for example, then it's the square because the square is what's, has 4 points and nothing else does. So this is a way of selectively applying things to nodes in a hierarchy. And we're going to define two convenience methods, which is basically, is something a leaf or is it not a leaf? So if it's a shape, we're going to say basically it's always a leaf. But if it's a group, it's not a leaf. So since group is more specialized than shape, is a subclass of shape, when you have a group, this method gets invoked and it returns nil. If you have a polygon shape, which is not a group, this method gets invoked and it returns t. Because polygon shapes are not going to have children. Only groups have children. Let's make another little convenience function which randomizes the size of a shape between low and a high value. So it just basically creates a value between low and high, and then it scales that transform of the shape by that scale. So it's going to be a uniform scale. That's why we only need one value, not a point. So if we take one of our old friends here, the triangle group, and if we decide we're going to go through all the hierarchy. We're just going to grab the first object in the shapes of the scene because we know that's our root node. And we apply a function which randomizes the shape between 0.5 and 1.5 and has a test of is it a leaf. So it only applies to leaf nodes. So this will happen for every hexagon shape in here, but not for all the intermediate groups which are in the tree. So if I evaluate this, you can see each of the hexagons changes shape, changes size, but it doesn't actually move. If you look, you'll see they stay centered at the same spot, even though their sizes change. Now, if I go back to my original shape, if this time I omit the test, I'm not putting the test in for do hierarchy, this test here. So it'll apply it to every shape and every group as it goes along. So all the intermediate groups are also going to be scaled, and we'll see what that does. So you can see the triangle, the shapes actually move around because the intermediate groups are also being scaled, and that's affecting the positions of their children. So this gives us an idea then. Let's try randomizing not just the scale, but the translate and the rotate and the scale of our shapes, of a given shape. And we do it by jittering, and jittering is basically randomizing by a small value. So we say jitter translate, and it translates the existing transform by a random number between the jitter values between plus and minus x and y of the jitter. So this will basically slightly randomize the translate, rotate, and scale of a given shape. Now, we decide to do one more generalization or elaboration of our recursive group method, not method, function. We just call it make recursive group 2. And before it takes a scaling, but this time it also takes a translate, a rotate, and a size. So it does the same exact thing recursively, except it also does a jitter, translate, rotate, and scale at every level. So let's see what this does. So here's one where I call it Wobbly Cross. So basically, yeah, let's just jump ahead. Okay. Let's make a Wobbly Cross. So this is our Wobbly Cross, because we told it to basically jitter translation and rotate by 10. It does no jitter in translation, that's 0, but it rotates by 10 degrees, and it rotates every group and shape by between plus 10 and minus 10 degrees. Sorry about that interruption. So the Wobbly Cross basically does a jitter by no translation jitter, but it does a 10-degree jitter, so it'll vary the rotation of the shapes between minus 10 and plus 10 degrees, and it'll scale them down by 0.5. So this is what we get when we take our cross pattern and we do the Wobbly Cross version of it. And if I make a function called randomize leaf sizes, which goes through the hierarchy of the group, I don't know why it's formatted this way. There we go, that's better. And that's better. And so this will randomize the leaf sizes, and this will randomize all of the nodes, including the intermediate groups. So if we make a Wobbly Cross, you can see each time it's different because it always has different random numbers. And if we randomize the leaf sizes, you can see the sizes but not the positions of the squares are changing. But if we randomize the node sizes, that means the squares as well as all the intermediate shapes, you can see that their positions change as well. All right, so that was a little overview of hierarchies and the fun you can have with them, and self-similar shapes and fractals, and using recursion to create geometry in Lisp. All right, see you next time. Goodbye. Hello and welcome to our first post-credit scene. As I was reviewing the tape, I'm really old. As I was reviewing the video, something occurred to me that in our first function that we defined, make row group, it might be fun to show how to do that with a loop macro that we talked about in a previous lesson. So in the original version, we have a variable, we create a list called row, and then we loop through n times, and we push an instance of group onto that row. So we push this instance of this group onto the row, and then we use that row as the children of another group, and then we return that. So I just thought it might be interesting to see what a version might look like with a loop macro. And it's the exact same thing, it does the exact same thing, but it's sort of more functional, and not functional, but straightforward in that, you're not storing intermediate values and then having to use them afterwards. So we just literally from the top say make instance a group. If children are going to be looped for I to n, collect, make instance a group, the children is the shape, and the instance, basically you scale it by the spacing so that it moves along in the direction that you specified. And then collect, remember, creates a list internally and returns it. So that list goes into the children of our main group. So just a little bonus feature for those who stick around till after the credits. And enjoy. See you next time.